So here are the book's instructions for predicting molecular geometries. Draw the Lewis structure. Find the total number of electron groups around the central atom. Determine the number of bonding groups and the number of lone pairs. And then this is ridiculous. Refer to table 11.1 to determine the electron geometry. Well, that's not going to work on an exam because I am not giving you that table. So that's bad advice. Think about how balloons would arrange themselves, and imagine that the lone pairs are invisible balloons. And if you need an excuse, tell whoever complains about you spending money that your teacher told you to go buy balloons and play with them. You can do it with gumdrops and other things as well. So let's practice. Predict the molecular geometry and bond angle of ClNO. Well, first thing, Lewis structure. Chlorine, nitrogen, oxygen. Without any additional information, I'm just going to go with the same order that was given there. That puts some more electronegative elements on the outside. It turns out it actually doesn't matter at all for this one. Next step in Lewis structure is number of valence electrons. Chlorine has 7, nitrogen has 5, oxygen has 6. So I believe that's 18, right? So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. I need to satisfy the octet rule. I don't have boron or beryllium here. So oxygen is the one here that's missing electrons, so I'm going to take a lone pair from nitrogen and have nitrogen share those with oxygen. Okay? Octets for everybody. So that was the first step, Lewis structure. Now what am I going to do? Am I going to look at the chlorine? I want to look at the atom that's in the middle, right? I'm going to look at the middle one, the center one, and say, well, how many electron groups are there? 3. Single bond is one group, a double bond is one group, a lone pair is one group. 3 groups. What shape does 3 balloons make? Trigonal planar, right? A flat triangle. So what are the angles in a flat triangle? 120. 360 divided by 3. So this is my electron geometry. The molecular geometry, I need to make one of these be a lone pair, right? So I'm going to make this the lone pair. Bit of a lopsided lone pair. What does it do to this angle? Is this guy, does he hate the lone pair more or this other bonding group? Hates the lone pair. So this is going to be a little, ooh, that's a really bigger greater than sign. That's going to be a little bigger than 120. And this one is going to be less than 120 degrees. What is the name of this shape? The molecular geometry. Bent. The molecular geometry is bent. Because the lone pair is invisible. Let's do I3 minus. I'll put the 3 I's in a row, I guess, right? And we have 3 iodines. They each have 7 valence electrons. And the -1 charge means I have to add an electron. So that gives me 22 electrons. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have another lone pair. We're going to throw that on the central atom. Can iodine handle an expanded octet? Yeah. It's in period 3 or larger. So we'll just kind of sneak that in there. So I'm looking at the central atom. How many electron groups? I have a bonding pair, single bond and a single bond, that's 2, and a lone pair, and a lone pair, and a lone pair. 5. Got to get the counting of the electron groups down. I know it's confusing, but that is like the key to the whole thing. 5 groups. Ooh. 5 electron groups. What shape did 5 balloons make? Trigonal bipyramid. It's more than the tetrahedron and less than the octahedron. Oops, that did not go very well. So that's my my electron geometry. But I have some lone pairs. Right, I've got 3 lone pairs, and so I need to make 3 of those into lone pairs. There's more space around the equator, and so that's where the lone pairs are going to be. So I'm going to make that into a lone pair. And I'm going to make that into a lone pair. And I'm going to make this one into a lone pair. They have more space there than if any of the lone pairs were at the top or the bottom. What's the name of that shape? Linear. Okay. Drawing these things on paper can get kind of tricky. So they've got this. The tetrahedron is the one that is most common, and that's going to carry over into OChem. And so, like, if I was drawing methane, I would put one of the hydrogens straight up, and I would put one, kind of at a 109.5 angle. These are all in the plane of the screen. And the other 2, one's going to stick out at us, and one's going to be behind the screen. So the one that's sticking out at us is going to be a wedge. That's like jumping out at you, right? And the dashed line is the one behind. You will need to draw some of these things on one of the worksheets. I am not looking for perfection. I am looking for, did they try? If you show me this, I'm going to say that's wrong, because that looks flat. This, even if you get it all wonky, I can tell that you were trying, right? What if we have more than one central atom? More than one interior atom? Well, there's lots of molecules like this. What we would do is we determine the geometry around each of those. And this is something that comes up in OChem. So for this molecule, we're going to look at the nitrogen over here. That one has 3 bonds and a lone pair. So 4 groups, tetrahedral electron geometry, but the lone pair makes it trigonal pyramid. This carbon has 4 single bonds, no lone pairs. 4 groups, tetrahedral. This one has 3 groups, right? No lone pairs. 3 balloons make a trigonal planar. And over here, this has 2 lone pairs. It's this guy over here. I should have been over here this whole time. This guy has 4 groups, but 2 lone pairs. So 4 balloons makes a tetrahedron, and you make 2 of those invisible, and now you have bent. Is it kind of like a blueprint? A little bit. I mean, we're trying to sketch something 3-dimensional on a 2-dimensional piece of paper, and it's hard. It is. It's hard. So predict the geometry around each interior atom in acetic acid, make a sketch of the molecule. So there probably will be a question on the next exam that asks you, gives you a molecule that has more than one interior atom, and it's going to ask you about geometry on some of the interior atoms. So I wouldn't give this to you like this, because this is not really the Lewis structure. So I'm going to do the Lewis structure so we can see a little better. So if you're given something like that. So this first carbon, how many groups does it have? 4. 4 single bonds. 4 balloons make tetrahedron. Are there any lone pairs? No. So that one is a tetrahedron. What about this carbon in the middle? How many electron groups? 3. A double bond is 1 group. What do 3 balloons make? Trigonal planar, a flat triangle. Are there any lone pairs? No. So that one's trigonal planar. And oxygen. How many groups? 4. Tetrahedron. And then 2 of those balloons are invisible. So this is bent. A lot of times when we draw the Lewis structure, these end up being opposite each other, and so we can sometimes think, oh, well, it's linear. No, it's not. It's bent. Okay, so now I'm going to try to draw this. So there's the oxygen, and there's the hydrogen, and this is carbon, and here's our double bond with the oxygen, and single bond with the carbon. The idea is try to get as many things flat in the plane of the screen as possible. And then this guy is a tetrahedron. So I'm going to have one over here that's also in the plane, and then I've got one guy that's jumping out at us, and another guy that's hiding behind the screen. And I will not grade you on drawing something like that. What's the molecular geometry around nitrogen in CH3 and H2? Well, the first thing is we need to have a Lewis structure. And for the sake of time, I'm just going to throw that one out here real quick. To answer this question, what's the molecular geometry around nitrogen? We first ask ourselves, well, how many electron groups does nitrogen have there? 4. 4 balloons do what? They make a 4 tetrahedron, and one of the balloons is invisible. So what shape is that? Trigonal pyramid. I'll just write it with the fat line. Trigonal pyramid! Okay.